Yeah, I still have them, but I'm not using them. Yeah. Still kind of hurts. Thanks. Yeah, it's pretty annoying having to use those things. All right, let's go ahead and get started. I'm going to finish up topic 5 today, and we'll spend a lot of time in R. I have a lot of good simulation stuff in the topic 5 script that I want to be sure we see. So I want to spend a fair amount of time over there. So where we left off is we talked about the Bootstrap as a kind of distribution-free, or for the most part assumption-free way of approximating an arbitrary sampling distribution. When we do inference, we have to have a sampling distribution. There's some parameter that we want to estimate, like a mean or a median or a standard deviation or a ratio of medians. And to do it, we collect data, we compute a statistic that estimates that parameter, and then to do statements with confidence, p-values, confidence intervals, we need a sampling distribution of that statistic. Bootstrap is a general way to approximate those. Just as a reminder, this is slide 6 from topic 5, and it's the now familiar Hotelling's t-squared test. This was that statistic that we saw for testing a particular mean vector. So I'm about to show you how to use the Bootstrap for hypothesis testing. And before we do that, I want to reiterate the basic idea of hypothesis testing. When we did Hotelling's t-squared, we had in mind a null hypothesis that the mean vector equaled a particular mean vector. So maybe we have 5 measurements of, or let's say, angles off from a target calibration or something. We have variable 1, and if it's off in a positive direction, we have a positive number. If it's off in a negative direction, we have a negative number. So we have 5 of those for some fancy instrument at Boeing. And we want to test, are the variables out of calibration? Do they not equal 0? The deviation for all 5 should be 0. It'll vary a little bit from measurement to measurement. So I want to test and make a statement with confidence, a decision with confidence about, is there a problem? Is the mean not equal to 5 zeros? The way we do that with hypothesis testing is we say there's a null hypothesis and an alternative. And the null in this case would be that the mean vector, call it mu0, is equal to what I specified that I think it is. So in this case, mu0 would be 5 zeros. It's just the null, under the null hypothesis, what's the mean vector? Then we compute a test statistic, and to get a p-value, we need the sampling distribution of our test statistic, but specifically, we need the sampling distribution when the null hypothesis is true. And that's the result that we had for t-squared. Here's a sensible statistic for testing the null hypothesis that mu equals mu0. You can assign a p-value to how strongly your data do not support mu0 by comparing to this null sampling distribution. Let me draw you a real quick picture. In the univariate case, let's suppose that we have univariate measurements and they're normal with mean mu and standard deviation sigma. So these are pH measurements from samples from our lake. Then suppose we wanted to test, is mu equal to a particular number? Call it mu0. And we'll consider a two-sided alternative that mu is not equal to mu0. In order to test this set of hypotheses, we would need to collect data. So here's a random sample of pH measurements. And on the basis of those, we compute a statistic, x bar. We might also compute S. And my t statistic, the test statistic, is estimate minus the mean under the null divided by the standard deviation of the estimate, t statistic. We said earlier that the subtraction of mu0 there is there because we're trying to force this to be something that follows a particular distribution when the null hypothesis is true. If the null hypothesis is true, then the distribution is indeed centered at mu0. So what I need for t is the distribution of that statistic when the null hypothesis is 0. And it's a t distribution centered at 0. Just to reiterate what I meant to say with all of that, the key to hypothesis testing is we need the sampling distribution of our statistic under the null hypothesis. So now let me go back to Bootstrap. Last time I told you about the Bootstrap as a general way to approximate any old sampling distribution. And we used it to get a confidence interval. If we had our data x1 through xn, we could get a 95% confidence interval for its population mean by using the Bootstrap. So for each of a bunch of times you sample with replacement from your data, for each one of those kind of pseudo samples, you compute your statistic. In this case, we might compute x bar. And then if you make a histogram of your B statistics, a 95% confidence interval is given by the 2.5th percentile and the 97.5th percentiles of that histogram. So essentially what we've done is taken just a data set and applied this resampling technique to get an approximate version of the sampling distribution of it, of the statistic. And then once we have that, we can get confidence intervals. What I want to show you now, though, is how do you do this to get p-values. You can use the Bootstrap for intervals or p-values. There's an extra step to the hypothesis test track. So let me go through this slide with you. This Bootstrap material in the notes is in the context of likelihood ratio tests. That's one way of doing tests. But we can interpret this for any old test. So the null sampling distribution of a test statistic is known in some cases, but what if we don't know the sampling distribution of our statistic? The likelihood ratio stuff, maximum likelihood things, we generally know the sampling distributions we need if we assume our population distribution is normal or if we have a really big sample size. So in small sample cases or non-normal data, we would like to be able to do inference, p-values and confidence intervals that don't require those assumptions. So when we're in that kind of case, parametric inferences may not be reliable. Bootstrap is an alternative. The key to doing the Bootstrap for hypothesis testing is that we're again going to do the resampling trick, but we have to make sure that after resampling, the sampling distribution we're approximating is the one that holds when the null hypothesis is true. That's what I was trying to underscore from the t-squared stuff. We need the sampling distribution of our statistic when the null hypothesis is true. So here's what we would do in the context of a t-squared test. Suppose we have multivariate data and we want to test the null hypothesis that the mean vector equals some particular mean vector. 5 zeros or whatever it is. And we're going to use, say, the t-squared statistic, but we're not comfortable with the multivariate normal assumption. So the analytical result on slide 6, we don't trust that, because that only holds if the data were normal. So I'm going to use the t-squared statistic, but I'm going to use the bootstrap to get the sampling distribution. Here's how it proceeds. First, you compute t-squared on your observed data. That's your observed test statistic value. When it comes time to computing a p-value, we're going to ask how likely would it be in some reference distribution to see a statistic like yours or even more extreme. That's the question that the p-value quantifies. So we compute that, and then we're going to do the bootstrap. But before we do the bootstrap, this is the new step. We have to first transform the data to force the null hypothesis to be true. So what we're going to do is we're going to take our x1, x2 up to xn, our data set. We're asking, is the null or is the mean in the population equal to a particular mean? What we're going to do is take each variable and shift its values so that its mean does equal the null hypothesized mean. We're going to force the data by shifting them to have the null hypothesized mean. So we're forcing the null hypothesis to be true, which means when we do the resampling, that histogram that we look at of statistic values will be statistic values that were generated under the null hypothesis. This trick here of transforming the data before doing the resampling enables us to get the null sampling distribution. And that's what we need for a p-value. So this stuff here, I'm taking my data were the xj, x1, x2, ... xn. And instead of xj, I'm going to use, when I do the bootstrapping, something called xj0. And that's just xj where I subtracted the sample mean vector. If you take all your variables and subtract off the sample mean vector, they'll all have an average of 0 now. And then adding back mu0. So I subtract the sample mean to make it be centered at 0. And then I shift it to make it be centered at mu0. Draw a small little picture here. We have data n by p. So we have variable 1, variable 2, variable p. And inside our data set, there's the first instance of variable 1, second instance of variable 1, nth. Here's variable 2, and so on. If you were to take variable 1 and compute the average of its column, you'd have a number that we could call x bar 1. That's the sample average of the first column. So there are these sample averages of each column. My null hypothesis is that mu is equal to some particular mu. There's p population means in that mean vector, and I'm hypothesizing a specific value for all p of them. In order to make my data as if the null hypothesis were true, I need to shift it so that instead of having averages of the variables equal to those x bars, the averages equal the mu0 values. In the slide, what what I wrote out was xj0 is xj minus x bar plus mu 0. So think of xj as a row. It's one individual's p measurements. I'm going to replace that row with what happens if I say that row minus the sample means, and then plus the null mean. If you do that to every row, then the average of each column is going to be the mu 0 value. This is all about transforming the data so that the null is true. Bootstrap is just a general technique, resample, and it'll approximate any old sampling distribution. So before we apply it, we need to force our data to be in accordance with the null hypothesis. But step 2 then is exactly like what we did with the confidence interval. It's just the bootstrap itself. We sample with replacement from the now transformed version of our data. So for each of capital B times, I'm going to create a bootstrap sample. If I have n individuals, my bootstrap sample is going to be n individuals. And they were sampled with replacement from my original n. But these were also sampled from the null transformed data. Okay, so now I have, for each of capital B times, a bootstrap sample of size n. And what I want to do is compute my statistic for those data. Because the sampling distribution stuff is about what's the distribution of your statistic. How would you expect it to vary from sample to sample? That's how you gauge, is it big enough to reject the null? So we observed this original t squared. Now inside the bootstrap loop, we're going to compute t squared for every single one of our capital B bootstrap samples. So the bootstrap P-value or hypothesis test. We have data. We don't know what the distribution of our data are, so I'm not going to use the F statistic for a t-squared test. But let's go ahead and compute the t-squared statistic. It's in x bar minus mu 0 transpose S inverse x bar minus mu 0. Because we're going to test the null hypothesis that mu equals mu 0. That's my test statistic. And for a p-value, the p-value is the probability if the null hypothesis is true of seeing a test statistic like ours or even more extreme. A t-squared statistic as or more extreme as the one we originally observed. That's the definition of a p-value. If the null is true, what's the probability that you'd see a test statistic as or more extreme as yours? So if it's a small number, first of all, it's going to be a probability. It's a number between 0 and 1. And if it's sufficiently small, then that's kind of a roundabout way of saying that the null hypothesis is probably not true. If it'd be very unlikely to see what you saw if the null were true, then that's evidence to say, well, the null is probably not true. So for the bootstrap, we did two things. First, we transform to make the null true, to force null true. And then we bootstrapped. And that gave us new t-squared values. So there was a t-squared 1, a t-squared 2, t-squared capital B. For every single bootstrap sample, I computed my t-squared statistic. Then the p-value. So if we picked up all these t-squared statistics and made a histogram of them, here's our t-squared way up here at the very beginning. And I would put my t-squared up against the histogram. And the p-value would be the area to the right. That's an approximation, at least, of the probability, if the null hypothesis is true, that you'd see a test statistic like yours or even more extreme. So let me show you this in action. This is the topic 5 script. I showed you last time a quick illustration of the bootstrap for confidence intervals. So here's an illustration of basically what we just talked about. May have a problem here. So it looks like they deprecated this package that I've been using. I think there's an alternative function in the mass package called mvrnorm. Let's see. What I'm doing right now is setting up a simulation. We're going to simulate some data and then show what the bootstrap t-squared test looks like. All right, so I'm going to use the mvrnorm function from the mass package to simulate some multivariate normal data. I need to tell it sample size, comma, mean vector, comma, covariance matrix. And my code is ready for that. Okay, so here I'm going to say, let's simulate some data. It's a small sample size, n is just equal to 10. There's only 3 variables, so a relatively simple scenario. Multivariate data, but my sample size is only 10, and I have 3 columns. This is just making up the parameters of the simulation. We could make these be whatever we want, but I'm saying mu1 is -1, mu2 is 0, and so on. These are the population standard deviations. This is the population correlation. So doing these calculations and then plugging them into mvrnorm will give me a 10 by 3 data set. Just need to fix that and that. So there's my simulated data. We are going to test a null hypothesis. I simulated from a particular mean vector, just made it up. And now we're going to test this particular null hypothesis. Might the mean vector be -0.5, 0.5? It's not. It's really -1, 0, 1. But we're playing pretend. It's like we saw data, and I'm curious, is this the mean or not? Mu0 then, I'm defining the object mu0 to be the vector containing the null means. Here is an illustration of the Hotelling's t-squared test. I've been saying the bootstrap is appropriate when either you have a non-normal population or you have a really small sample size. In this case, we have multivariate normality for the population because we simulated it that way. So there's nothing wrong with doing the t-squared test in this case. This is just an illustration of the t-squared test. Step one is to compute the sample statistics, x bar, capital S. It's the vector of means and the covariance matrix. This is the t-squared statistic, n times x bar minus mu0 transpose, S inverse, x bar minus mu0. And then the p-value, where did that come from? Let me walk through this real quick because you do need to see this. That's the t-squared value. The test statistic value is 165. I know the null hypothesis is not true in this case because we simulated from a different mean. So this is my test statistic. I should get a p-value that's small. I should reject the null because the null is not true. But in order to actually make a decision, I need a p-value, not just the t-squared. That's 165. Is 165 big? It all has to do with respect to what? So we want a probability. What we know about the t-squared test from earlier in topic 5 under the null hypothesis, the t-squared statistic is distributed as this n minus, is it n minus 1 or n minus p first? N minus 1 times p divided by n minus p times the fp n minus p distribution. So a p-value for the t-squared test is what's the right tail probability in this mess evaluated at my t-squared. R doesn't have a function for that red mess though. It does have a function for the F distribution. So to get a p-value in R, what we would actually do is 1 minus the tail probability of the F. Let's see. Hold on. Yeah, of the F. Evaluated at n minus p over p n minus 1 t squared with p and n minus p degrees of freedom. What I just wrote is what's in the R script. And the first time you look at it, you'll be confused. Because in the slides, we have this result. T squared has this funky distribution. That's equivalent of saying t squared times n minus p divided by n minus 1 times p has the F distribution. So if you take the messy constants and divide them over to this side, then you can say that messy constant times t squared is F. That's what this is doing. Right tail probability for the F evaluated at the divided by the constant times t squared, and the F has the p and n minus p degrees of freedom. So this is now a p-value for this particular test. Very, very small. Using the parametric t-squared test. Now let's see what the bootstrap looks like. The bootstrap should also give us a small p-value. It's a valid way to do the test, but we're not going to take into account the multivariate normality of our data. This, what follows, has no assumption of normality or anything in it. Step one is transform the data to force the null hypothesis to be true. And the code may look a little more complicated than you would hope. If you play with that line of code, you'll see that it's doing what we have in the slides. It's taking every column, subtracting off the column means, and then adding back the null means. After doing this, whereas the column means of the original x were those things, the column means of the transformed guy equal mu 0. So there's just a slight rounding thing. Let me round these. x0 has been transformed so that its means are the null means. And then this is just like we did with the confidence interval. It's a loop over bootstrap samples. I'm going to make there be more than 250. So let's do capital B equal 2,500 bootstrap samples. I'm creating an empty container of length capital B in which I'm going to put each bootstrap statistic value. Then looping over all the bootstraps. Sample with replacement from the transformed data. So this command right here is going to create x underscore b that is 10 by 3. It's a new data set. It's obtained by sampling with replacement from the null version of our data. And by sample with replacement, what we mean in a multivariate case is you sample the individuals. The data set is 10 by 3. So when we say sample with replacement, what do you mean? Do you pick cells with replacement? Or do you pick columns or rows or what? What we do is we pick rows. Because we want to, the bootstrap idea is to sample individuals. Each individual for us is a row. So this highlighted command is saying, go get x0, that's the transformed 10 by 3 matrix to make the null true. And then remember that we use square brackets to subset an array. With a two-dimensional array, we have square brackets, something telling it which rows to bring out, comma, which columns do you want. In my command, I have something for the rows, but nothing for the columns. So this is saying, give me these specific rows and give me all columns back. So the sample command, sample the numbers 1 through n with replacement. If you run sample 1 through n with replacement, let me just take this over and run it. That's one possible set of output. It's sampling the numbers 1, 2, ... 10 with replacement. So first we pick the first one, then the fifth one, then we pick the first one again. Notice that number 2 and number 3 were never picked. But these are now indices indicating which rows of the data set to go get. To do bootstrap, you sample the individuals, which in our case means the entire rows. These numbers are which rows we're sampling. So that whole command, xb, is going to be 10 by 3, where every row was sampled from the rows in x0 with replacement. Once you have your bootstrap data, 10 by 3 array, you want to compute the statistic and store it. So that's what this is doing. Compute x bar for these simulated data, compute the covariance matrix, and then compute t squared. And notice that I'm putting this particular t-squared value in the bth element of my container vector. So at the end of this whole loop, t squared b will be a vector of t-squared statistics. Last time when we did the bootstrap, we had a vector of x bar values. That's not good. Let me increase the sample size a little bit. Okay. I changed the simulation just a little bit. The p-value from the t-squared test is now this number, which is even smaller than before. And then I ran the bootstrap code. So now this t squared b is 2,500 long. And it contains 2,500, here's the first 10 of them, t squared statistics. These are all t squared statistics that you would expect if the null hypothesis was true. Our t squared statistic, T2, was 208. So just looking at the first few of these, it's clear that our statistic is extreme, most likely going to be computed as extreme relative to the null hypothesis. We could make a histogram of all of these, and that would be our null sampling distribution of the t-squared statistic based on the bootstrap. If we overlaid the funky F distribution, it would follow it very closely. But we got this one without any assumption of a normal distribution. The p-value is then put your t-squared statistic up against this distribution and compute the right tail area under the curve. That's what this is doing. T squared b greater than or equal to T2. I can get rid of this. That's not necessary, I think. Yeah, I do need to do that. This command right here is going through all the 2,500 t squared statistics and asking, are you bigger than or equal to our t squared? That's going to give us 2,500 trues or falses. So for the p-value, I want the proportion of trues. So if I compute the average of a bunch of zeros and ones, that's the proportion of ones. My p-value, according to the bootstrap, is what proportion of times is our null simulated t squared bigger than or equal to our observed t squared. It'll probably be basically 0, yeah. So Bootstrap is a general way to approximate sampling distributions. You can use it to get confidence intervals. You can use it to get p-values. In order to use it for p-values, the trick is to first transform the data to force the null hypothesis to be true. Then you apply the resampling, and you compute a p-value as the area at or beyond your observed statistic in the resulting histogram of bootstrapped statistics. So I know that was a lot to throw at you. I still need to keep moving. We've got a little more time left. And I definitely need to get at least partway through the confidence coverage. So all that stuff up to this point in topic 5 was about hypothesis testing. I want to make a formal decision. Yes or no, is there an acid lake problem or an acid rain problem in the lake at a stated level of confidence? An alternative way to make a confident statement about a parameter is with a confidence region. Instead of making a decision, I don't think the parameter equals this. Instead of that, we'll say, I think the parameter is within these bounds. And I'm 95% confident in that claim. This is a reminder of the univariate confidence interval case. Stat 101 says if you assume your population distribution is normal, and then if you want a confidence interval for the population mean mu based on a data set, this is a confidence interval. This is a 100 times 1 minus alpha % confidence interval for the population mean. X bar, or the estimate of mu, plus or minus a critical value from the t distribution times the standard deviation of x bar. Estimate plus or minus a cutoff times the SD of the estimate. Based on your data set, your n observations, you compute x bar, you compute s, and then you do this calculation and you get a lower bound, comma, upper bound. And you can say about that, this is a 95% confidence interval for mu. If pressed, what does that really mean? What you would say is this interval was constructed in such a way that 95% of the time it will contain the truth. 95% of all 95% confidence intervals will contain the truth. My particular interval from 1.02 up to 4.3, it may or may not contain the truth. The truth is some number, and my interval is just these two numbers. So it either contains the truth or it does not, and I have no way of knowing. All we can say with frequentist statistical inference is, if you were to redo my study many times and construct a confidence interval like mine, 95% of the time it would have contained the truth. So now let's translate to multivariate world, and we have a multivariate mean vector now. We want a p-value for testing whether that equals something, and now we want a confidence region. We already know how to do this based on things we've seen, it turns out. This first line is something we know from previous portions of this slide presentation. This is the t-squared statistic, and we know that its distribution is this scaled f. So the probability that the t-squared statistic is less than or equal to the alpha critical value, the number that puts alpha to the right, is just 1 minus alpha by definition. This quantity right here is just the 1 minus alpha percentile of the sampling distribution. So for a given choice of mu, if you wanted to ask, is it within a confidence region, this is a good place to start, because this defines all mu's that are within 1 minus alpha of the mean. That wasn't right. Let me jump down a little bit. A confidence region for mu is defined as the ellipsoid containing all mu's such that this distance is within that kind of critical distance of our sampling distribution. So that statement at the bottom is a confidence region for mu. And by region, we mean multidimensional. If p is equal to 2, for example, So confidence region, if P is equal to 2, we're outlining an ellipse. Here's the mu1 axis, here's the mu2 axis. And we're considering where is the dot that represents the real mu1, mu2. A confidence region would be like this ellipse. And we could say I'm 95% confident that the real mu1, mu2, wherever it is inside my ellipse. When we did the univariate t stuff, what we are saying with a 95% confidence interval is I'm 95% confident that mu is in my interval. A confidence region is an ellipse or an ellipsoid about which we say I'm 95% confident the vector mu is inside. It's a very similar interpretation. It's just that confidence regions are multidimensional things. So a confidence region is trying to capture all of the mean components simultaneously. What's coming, jump ahead just a little bit here. What's coming is what if we want confidence intervals for each of the mean components separately? The confidence region tells me like an ellipsoid within which I think mu is. Alternatively, we may want a separate confidence interval for mu1 and for mu2 and so on. And I'm not going to be able to finish this today because this requires a little saying. Let me just show you a picture. And I'll wrap this up on Friday. Here's a two-dimensional simulated example, like I just drew in the whiteboard. mu1 and mu2, horizontally, vertically, respectively. And we have data on the basis of which we're wondering where is the dot that is mu1, mu2? What's the real population mean? What topic 5 is going to give us is a handful of ways to construct confidence regions for the mean. A multidimensional confidence region is shown by the ellipse. And that's a 95% confidence ellipse. We can say I'm 95% confident that the dot, mu1, mu2, the pair, is inside my ellipse. The technical intricacies of that, like in the t-based confidence interval, still apply. I don't know if my ellipse contains the truth, but 95% of all ellipses constructed in this way will contain the truth. And then what we'll see on Friday is what if we want separate intervals for each of the mean components? We're going to have two ways to do that. The red lines are one way. They would give me, if it turns out, if you just take like the shadow down the ellipse, wherever those hit on the axes, that defines a 95% confidence interval of a particular type. And simultaneously, if you go across to the y-axis, that's also a 95% confidence interval for mu2. Those end up being wider than necessary, so we can do a little better by using the blue dotted ones. I'll show you those on Friday. But the main distinction here is, do you want a region, like an ellipsoid, or do you want separate intervals for every variable component? The trick with doing separate intervals for each component is that now you're kind of doing multiple confidence statements. And if you've had, say, STAT636 or something like it, maybe you've been exposed to the idea of multiple testing, where if you do multiple hypothesis tests at the same time, you accumulate likelihood of making a mistake of some kind. So you have to be careful. And a similar dynamic is here. If I want an interval for this variable and for that one and so on, we have to be careful with the way we construct them so that they have the correct interpretation. Okay, I'll wrap it wrap it up there. Thanks.